All right, so I'm going to do some review of Big O and how we can demonstrate it using the different methods that we've learned. So first of all, I'm going to use the definition of Big O that requires you to find constants, right? Constants C and N naught. And so there's two ways of doing this. There's what I call the harder method, and that's where you start by picking a C value and then you find an N naught that makes this inequality true. So how we can do that is we can start by identifying a dominant term in our function. And we can see here that 3n squared is our dominant term. And of course, we have that little coefficient of 3 right here. So now we need to choose a coefficient c that makes f of n larger than this dominant term, f of n being our n squared right in here. So we'll go ahead and we'll pick let c equals 4, right? That is larger than 3. Technically, you can choose whatever c you want. You could have c equals 5 or 6 or even 100, right? Whatever you want. But if we pick a value that's smart, it'll actually save us a lot of work later on. So let's just pick c equals 4. We'll just go one higher than that coefficient. All right, so now we need to set up the inequality right here, and then we need to find an n naught that makes this inequality true for all n greater than n naught. So I'm setting up the inequality right here. So that is t of n on the left. This one is going to be less than or equal to c, which is 4, times our f of n, which is n squared, for all n greater than n naught. So we need to find an n naught where this inequality is true. And so what we're going to do is we're going to start by kind of simplifying it down. So we see that we can subtract 3n squared from both sides. So that will leave us with 2n plus 1 is less than or equal to just n squared. And let's go ahead and move the 2n to the right side, which leaves us with 1 is less than n squared minus 2n. And so now we're not done yet. We still need to factor out the n here. And we're left with this little inequality with two parts. So if I can show that each of these individual parts is going to be greater than or equal to 1 for some, right, n larger than a value, then I can show that this whole inequality right here is going to be greater than or equal to 1 for some n. So I'm going to split that into two parts, a and b. Let's go ahead and start with a. So when is the inequality 1 is less than or equal to n true? Well, that is true for n greater than or equal to 1. All right, done. B. So now we need to show that, right, which values of n make this inequality true. We can go ahead and kind of simplify by moving the 2 to the left side, right? And so we get 3 is less than or equal to n. And this is true, of course, when n is greater than or equal to 3. So by using these, right, we can choose an n that works with both. We'll pick the greater one, of course. And so that makes this whole thing true when n is greater than or equal to 3. So we want to choose n not equal to 3. And of course, c is equal to 4. And we found our two constants. Therefore, right, t of n is going to be in big O of n squared. All right, so the second method, still using the constants definition, is what I call the easier method. And this is kind of the opposite of the previous one. We start by picking an n naught, and then we find a value of c. So what we need to do for this method is we need to set up what I call mini inequalities. So basically, for each term in t of n, right, that's this one, and this one, right, each of these terms has a coefficient, 3, 2, and 1 in this example. What we need to do is, with each of those coefficients, we need to show that this term is going to be less than or equal to something of the form f of n with that same coefficient. All right, so let me actually show you what I mean here. So I'm going to take this first coefficient right here, which is 3, and we're going to observe that, well, 3n squared, that first term, is less than or equal to 3n squared, right? Same coefficient, but now we're using f of n, right? And this is, of course, true for all values of n. We'll also observe that 2n, now the second term, is less than or equal to 2, the same coefficient, times n squared, or f of n, right? And this is true for n is greater than or equal to 1, right? It's a pretty simple thing to prove. Can I prove that 2n is less than or equal to 2n for n is greater than or equal to 1? Well, what we can do is we can take 2n and move it onto the right side, like so. And we can see that we're able to factor out 2n like that. And of course, we can divide it by 2, which gives us n times n minus 1. And so again, we can prove these two individual sides, right? So when n is greater than 1, of course, n is going to be greater than 0, right? So that's our little a part, right? N is going to be greater than 0. That is true for n is, of course, greater than or equal to 0. And then b, 0 is less than or equal to n minus 1. That is, right, able to become an inequality of this form right here. And so that is, of course, true when n is greater than or equal to 1. So we can show that this right here is going to be true for n is greater than or equal to 1, right? But that's pretty trivial. So we're just going to go ahead and assume that we can figure that out. All right, and now we come to the third term right here. And so we're going to have 1 is less than or equal to 1, right, times n squared, right, that f of n right there. And so when is n squared greater than or equal to 1? That is going to be true for n is greater than or equal to 1. All right, and so because we have these three inequalities, we need to choose an n naught that makes them all true. All right, so all of this is true for n is greater than or equal to 1. So let n naught equals to 1. And now we can set up that big inequality right here. So we'll go ahead and write down our t of n right here. That is going to be less than or equal to 3n squared plus 2n squared plus n squared, right, for n greater than or equal to 1. Right, we just showed that those little parts are true. Right, this is always going to be greater than that, that's always going to be greater than that, that's always going to be greater than that. So this inequality is true. All right, and now we just need to take the right side and kind of simplify that down to a form that fits c times f of n. So we do not want to touch the left side for this method. So we can see that we can add up 3, 2, and 1, those coefficients. All right, 3 plus 2 is 5, 5 plus 1 is 6. So we get something of the form 6n squared, which, hey, that kind of looks like c times f of n, right? And so we can see that our c is equal to 6, and again, our n naught is equal to 1. And so these are our final values right here. So we can also demonstrate that something is in big O of something else using the limit definition up here, right? And so we're able to set up this limit and just kind of solve it and then see if it's in this range to demonstrate that something is in big O of g of n, right? So this is a much more straightforward method. What we'll do is this is right here. This is our f of n in this case. And right here, this is our g of n. And so we'll set up our limit limit as n goes to infinity of f of n divided by g of n. So 3n squared plus 2n plus 1 divided by n squared. And so now what we're going to want to do is we're going to simplify that down, and we can see that the n squared is going to kind of cancel out, right? So we get 3 plus 2 divided by n plus 1 divided by n squared. And now what we can do is we can actually go ahead and substitute infinity into there, and we get something that looks kind of like this. Of course, that's going to give us 3 plus 0 plus 0, right, which is equal to just 3. And we know that 3 is, of course, in the range between 0 inclusive to infinity exclusive, right? Therefore, we've demonstrated that our f of n is big O of n squared. All right, so this is the value we want to focus on. All right, let's do that again. Down here, right, this is our f of n, and this is our g of n. And so we can set up our equation again, squared. And so we see immediately that we can kind of simplify this to just log base 2 of n over n. And now, unfortunately, if we try to substitute infinity, we get something of the form infinity over infinity, which is undefined. But we can rely on L'Hopital's rule, right, or L'Hopital's rule, where we can take the derivative of the top and the derivative of the bottom, and we will get the same limit as if we did that. So I'll go ahead and use L'Hopital's rule. And we'll take the derivative of the top, which gives us 1 over n times ln of 2. That whole thing divided by just 1. Right? Of course, that is just going to be the limit as n approaches infinity of 1 over n times ln of 2, which is just a constant. So if we substituted infinity into this, we would get infinity times ln of 2. And of course, that's just going to be infinity on the bottom, which gives us a 1 over infinity, which is going to be 0, right? And so we have this value of 0, and 0 is, of course, in the range between 0 to infinity, like so. So we've demonstrated that it is big O of n squared. So now let's focus on big omega, right? Big omega being that lower bound. And we'll start with the constants definition, right? And so there's two methods to do this one as well. There's this harder method, like I've said before, where you start with C and then you find an N naught. Here we do something similar, except we're going to pick what I call a matching term. I'll show you what that means. So here we have our T of n, right? And of course, our F of n right here. And this is our T of n. And we want to find a matching term in T of n, right? Something that is of the form n squared. And we can see we've got one right here. So let's go ahead and steal its coefficient. So we'll say let C equals 3. Again, this is kind of arbitrary, right? You can find any kind of constants, C or N naught, right, that make this inequality true, but it's much easier to prove if you are smart about it and pick good values for C and N naught. So, right, C could technically be like 2, C could also be 1, right? But picking C equals 3 helps us prove or demonstrate this pretty easily. So we'll go ahead and pick C equals 3, and then let's set up that inequality. All right, so now we have 3n squared plus 2n plus 1 is greater than or equal to C, right, times our f of n, right, for all n is greater than n naught. And so our goal is to, again, find n naught that makes this inequality true. So to simplify this down, the first thing we can do is we can subtract 3n squared from both sides, right? Because we picked that coefficient in a smart way, right? This cancels out nicely. And so we're left with just 2n plus 1 is greater than or equal to 0. All right, and we can go ahead and subtract 1 from both sides and then divide both sides by 2. And so n is greater than or equal to negative 1/2 when n is, well, greater than or equal to negative 1/2, right? So we can choose our n naught to be 1, right? Because 1 is, of course, greater than negative 1/2. So any n that's bigger than that will satisfy this inequality. Why did I pick 1? Why didn't I just pick 1/2? That's because c and n naught need to be positive constants. And so I could have picked n naught equals 1. I could pick n naught equals 2, 5, 500, right? It's pretty arbitrary, but n naught equals 1 works. So we'll go ahead and stick with that. And we found our two constants that demonstrate that our t of n is in big omega of n squared. So let me show you how to use that method again, but this time we're going to demonstrate that our t of n is in big omega of n. So let's go ahead and start off by looking for a matching term. Right, in this case, 2n is going to be our matching term. So we're going to say let c equals 2. Again, to repeat, right, this is pretty arbitrary, right? I am able to just even pick c equals 1, right, or some value, but letting c equals 2 helps us set up this inequality. All right, so now we got to set up that inequality. So 3n squared plus 2n plus 1 is greater than or equal to c times f of n. All right, and this is true for all n greater than n naught, and our goal is to find n naught where this is going to be true. So if you can see, because we picked that same coefficient, we're able to subtract 2n from both sides and effectively cancel out that entire term, right? We chose wisely. So we can go ahead and kind of work through this like so. And we get the inequality n squared is greater than or equal to negative 1/3. All right, what values of n make this true? Well, this is true for all values of n, right? Or all real values, rather. So we can pretty much arbitrarily choose any n naught that is positive. All right, so let's go ahead and just say n naught is equal to 1 again, and our c is equal to 2, and we found two constants that make this true. All right, so here's the easier method, method 2, again using this constants definition. So I'm going to set up many inequalities again. This time, though, I'm only going to focus on equal or larger terms when compared to our little g of n, or sorry, our f of n right here. All right, so you can see here I'm going to focus on this first term, and we're going to again make some observations. All right, so observe that 3n squared is always going to be greater than or equal to 3n squared, right? I'm taking that same coefficient, but I'm applying it to the function on the right. Right, this is, of course, true for all n, right? Those are equal. Now I'm going to look at the second term, and, well, is there a way that we can say that n squared is always going to be smaller than 2n? No, there isn't. So we are going to kind of ignore it. We're going to just make the statement that 2n is always greater than or equal to 0, and that is, that could be true for a variety of n, right? Of course, when n is greater than or equal to 0, that is going to be true. All right, and we're going to do the same thing with this one, right? There's no way that we can show that n squared is going to be always less than 1 for, sufficiently large n. So we're just going to kind of say that 1 is always greater than or equal to 0. And this is true, of course, for all n. All right, so we've demonstrated all these little inequalities are true for certain values of n. And now what we're going to do is, again, we are going to set up, right, our inequality and, of course, choose our n naught that makes them all true. So we can see that this is all true, right, for n is greater than or equal to 0. So let's just choose and n naught is equal to 1 again, right? This will all still be true for n greater than 1. And so now we can find a c that works. So we'll set up this big inequality again. So 3n squared plus 2n plus 1. That is always going to be greater than 3n squared plus 0 plus 0. Basically, we've dropped all of the lower order terms. And of course, this is just going to be 3n squared, like that, which is of the form c times f of n. So perfect, right? This is all true for n is greater than 1. And of course, we found our c right here. So c is equal to 3, and n naught is equal to 1, and we found our two constants. All right, let me show you this easier method again using that constants definition. So now we're going to show that this is going to be in big omega of n. And so step 1 is we want to set up these many inequalities. And so we'll start with this first term. So observe that 3n squared is always going to be greater than or equal to 3n, right? And this is true for n is greater than or equal to 1. All right, next up, the second term. We can also show that 2n is going to be greater than or equal to n, 2n, right? Because those are equal, and that is true for all n. And this last term, we cannot show that 1 is always going to be greater than n, for large n, rather. And so instead, we will kind of drop that, and we can show that 1 is always greater than or equal to 0, right, for all n. So we can choose an n naught that will make all these true. And if we choose 1 again, hey, that conveniently works. All right, so now we need to find c by setting up that inequality. N squared plus 2n plus 1 is going to be greater than or equal to c, right, times f of n. So we can take our little pieces, right? This is always going to be greater than or equal to 3n plus 2n plus 0 and 5n, right, is what that simplifies down to. So we have c as 5. So c is equal to 5, and again, our n naught is equal to 1. I'd like to reiterate both at the bottom and underline it so it's very clear what constants we've ended up with. All right, so now we can also demonstrate big omega using the limit definition, right? So we'll just set up this limit, and we'll find out if the resulting value is in this range. So this right here is, again, our f of n, and this thing on the right is our g of n. So we'll set up our limit as n approaches infinity. F of n divided by g of n. And we'll go ahead and divide each of those upper terms by n, giving us 3n plus 2 plus 1 over n. And that is going to, if we substitute infinity, that is going to give us 3 times infinity plus 2 plus 1 over infinity, which is, of course, just going to be infinity plus 2 plus 0, which is, of course, just going to be infinity, right? And we know that infinity is in the range of 0 exclusive to infinity inclusive. So there is our final value, and we've shown that it's in the range. So we've demonstrated that f of n is big, or is in big omega of n in this case. So let's do one more. So our f of n and our g of n, set up that limit. All right, and so we have n log base 2 of n over just n. And we immediately can see that, of course, this is going to grow larger than this. But we need to actually demonstrate that, so we need to work out this problem. So the n's cancel out, so we're just left with the limit of log base 2 of n. And if we substitute infinity, we get that, which of course is just infinity. And we know that infinity is, of course, again, in that range of 0 up to infinity inclusive. So there is our final value. So next we'll move on to big theta. So to use constants, right, and that definition, if big theta, what we need to do is we need to show that it is in big O of f of n and big omega of f of n, of f of n. And that will demonstrate that it is in big theta of f of n by definition, right? So big theta means that something is in both big O and in big omega. All right, and using the constants method, right, or the non-limit definition rather, you must show each of these separately. You must demonstrate that, and you must demonstrate that in order to demonstrate that. All right, so I'm not going to do that, but basically you need to set up both big O and big omega and demonstrate two problems essentially. However, it's much easier to use the limit definition for big theta because we don't need to do two problems. We can just work out one and check if it's in this range. So if we don't tell you which method you need to use, I recommend just using the limit definition because it's much more straightforward, it's much faster. All right, so I'm going to do a couple examples. So here we again have our f of n, and here we have our g of n. And so let's set up that limit and see what that evaluates to. So we got 3n squared plus 2n plus 1 divided by n squared. And that is going to be equal to limit as n approaches infinity of 3 plus 2 divided by n plus 1 divided by n squared. So now we can actually substitute infinity in here like so. And of course, that is going to become 3 plus 0 again, like we saw before, which just gives us our final value of 3. Right? And we see that 3 is in the range between 0 and infinity, both exclusive. All right, and for this last problem, we don't know if this is going to be big O, big theta, or big omega. So let's take a look. So we got our f of n and our g of n. So we'll set up that limit again. So n approaches infinity, n squared plus log base 2 of n divided by n squared. Work that out. So we can say that those n squares cancel out, right? So we get 1 plus log base 2 of n divided by n squared, like that. And we can actually pull out the 1 because the limit as n approaches infinity of any constant is still going to be that constant. So we end up with something like this, and we can see that this will result in something of indeterminate form of infinity over infinity. So we can apply L'Hopital's rule and take the derivative of the top and the bottom separately. So derivative of the top is going to give us 1 over n times ln of 2. That whole thing divided by the derivative of the bottom, which is going to be 2n. And that gives us 1 over the limit as n approaches infinity of 1 over 2n times n times ln of 2. And, well, if we substitute infinity in here, we get 1 over, basically 1 over infinity. And as we know that, it's just going to be 1 plus 0. And so we get the final result of 1. And 1 is in the range of 0 to infinity, both exclusive, right? Which means that it is in big theta of n squared, which also means that it is in big O of n squared and big omega of n squared. All right, so that's it for this little review. Feel free to let your instructor know if you have any questions.